All right, hi everybody. I'm Ethan Peck. I'm a director of data engineering at Zoominfo. And we're here to talk about next level data lineage, capturing insight by the record. Put another way, record level lineage.
Good. So Ethan is gonna start with his story and then we'll get into the architecture, design and solution aspect of it.
All right, so I want to start with a purely hypothetical situation that I'm sure many of you are somewhat familiar with. Let's say your company has put together a set of, let's say, mastered entities, right? So you have a very complex pipeline bringing together lots of disparate data, and you're trying to create an entity, and you're doing that maybe for your sales team, who's about to go reach out to a person and contact them to sell the solution that your company is selling, right? So you have your SDR, your sales development rep, very excited to make a call using this data. And he's going to try to call the CTO of a prospect company with this fantastic software solution. He didn't reach the CTO. He reached the director of HR, that guy in the background there, right? Wrong person. Well, that person does not care about the software solution that SDR was trying to sell. And so he's angry because somebody called him on his phone about a thing he didn't care about. So what is he going to do as retribution? He's going to post something on the internet, like, I'm unhappy with this scenario. Well, your company has a content team that's sitting there watching all of social media for good press and bad press and everything in between. And they are very, very concerned about seeing this bad press. And so they go and they talk to legal, compliance, and privacy. And guess what? They are not happy that there was the wrong information on their database and that their SDR went and spoke to the wrong person. And so then they come to you, the engineering team, and say, what happened? What gives? Fix it. So why do you care about this? First of all, despite the saying, not all publicity is good publicity. Also, it's a bad experience for your internal customer, the sales team in this case, and it's a bad experience for the prospect customer. The person who you wanted to reach might have actually wanted your product, but you reached the entirely wrong person. And finally, there's a bunch of legal and privacy implications, right? You're not allowed to collect someone's data in general without telling them about it. And if you have the wrong person's information, you didn't tell the right person that you had their information. So what do you do about this? Very quickly, I'm not going to read all of this. The point is, you're going to have to go through all of your systems. You're going to have to find all the past where all the data came from. So there might not be primary key, foreign key relationships. You're going to have to make a lot of ad hoc judgments to figure out how to join these tables together to try and trace back this one record all through the past. You're going to have to talk to a bunch of SMEs to find out, where did the data come from? Where did it go? How was it processed? What happened? You're going to then have to put all these findings together. You're going to then generate a report, all for one record. This isn't the 100 million records that you're fixing a giant. It is one record. Takes a lot of time for one person to do that. So let's talk data lineage.
I think most of you are aware of or familiar with the data set level or system level lineage, where you basically capture the metadata about the data processes and data set, where you get a high level view of system level connections or data set level connections. But the problem that Ethan described cannot be solved using this solution. And so data set here is just an abstract for data. It could be tables, set of tables, storage bucket, or third-party systems. And system being a data processing pipeline. And this is a very simplified view of the data set level lineage solution, where you have processes, data sets, input data sets, output data sets, and you have a centralized lineage system where the processes actually send in metadata, where it's stored and then later supplied to generate a view on demand when somebody wants to look at the lineage information of the systems. But again, this is dataset or system level lineage. Typically, solutions are having a centralized lineage repository where you store data using some data model. There are standard solutions which I mentioned here, which only support like single platform. And then there are open source solutions. So open lineage is very popular these days. It supports multiple platforms and also integrated with multiple platforms very well. But again, these are all dataset level lineage. But you cannot do something like this using a dataset level lineage. If you find a record with some problems and you have to trace it back all the way to the most upstream system, you cannot do that. You will have to probably go through a lot of analysis and multi-team collaboration effort and all that stuff. So how do we do it? What if you have a way to kind of link all these records beforehand, and then be able to query or maybe just get to one record and then trace it back all the way to the origin of that record. It could involve multiple upstream systems or many other external third-party systems as well. So again, these are two simple use cases. The first one is simple ETL or ETLT as I call it, where you do extract and maybe minimal transform and then you measure transformation. And then there is a complex use case where you have multiple systems as the upstream systems, and then you merge data from two systems and produce a data product, which is basically becomes your final output where you build your use cases. And this is where most of the problems occur, especially during enrichment phase where you marry two data sets together to form one record. But then how do we build it? Like we can just basically use the same design and architecture that people are using for the data set level lineage, which is creating a centralized repository where you capture all the lineage information, but this time per record, and then store it and then make it available. Or you can basically decentralize or do with like a federated approach where you don't have to copy all the records together in one system. You just basically link those records somehow logically and then be able to query those records on demand when you need it. Now, this is an novel approach. At least I'm not aware that anybody has tried it ever. I thought it could be done, and it's not that complex to do it. As long as you build some standard solutions or wrappers to make that happen, and the complexity is also low to moderate based on my experience. But let's assume for the timing that if we were to use the centralized solution to build record level lineage system, then this is how it would look like. You have the same data processing systems that would then have to send in, somehow join those records or link those records and then send the actual records along with the linkage to a centralized lineage system. And not to mention that those records could be polymorphic. That means the model of those records could be different, the schema could be different, then you will have to basically create a polymorphic lineage repository that would support different structures. And then yes, then you can generate a view which can query the records from that lineage system. But then it would cause huge data duplication. You will have to basically build and maintain a data management system, and it will also increase your storage cost. As I mentioned, the data model is going to be very complex, to accommodate records with different forms and shapes. So what I propose here is that, how about we don't create any centralized solution for this. We keep our data landscape as is. We keep our data processing systems and pipelines as is, but we provide those data processing pipelines the ability to link those records using something, and then when they persist the records after transformation or enrichment or anything, then basically the linkage will also be persisted with the record. So the linkage would basically stay with the records. And then when at a later point, when we need to query and trace back records all the way to the upstream systems, then we can easily do it. And this solution is better because it has no data duplication. You don't have to copy your records, and there is no central solution to maintain and build. and there is no additional storage cost as well. And the integration here, basically, you don't have to integrate with any system. You just have to enhance your pipelines a little bit to kind of create that linkage. Everything is still the same. I mean, you are already doing most of the heavy lifting in data processing anyway. And last point is, you don't need to invent or design a new data model. But then how do we do it? So there are two problems. How do we link the records? So what is that linkage? And then problem number two, if your lineage information is not in one system, then how do you query it? If it's like, attached with the records that could be stored in disparate or multiple systems, then how do we generate that lineage view? So let's look at the solution of the first problem, where how do we basically link the two records? So what I'm proposing here is the lineage ID. So lineage ID is, it's a unique ID across all systems for a record, meaning the record could exist in one system, and the parent of that record or the upstream two records from it was merged would also be the same, and so on. So the very first system would basically generate the lineage ID and associate with the record, and then when that record flows to the downstream system, it will be passed along with that processing step, and the downstream system would also retain and store that lineage ID. But then you have to map some additional piece of information with the lineage ID so that when records flow through, let's say, multiple systems, you have to know in each downstream system what's the upstream system that sent the record to the downstream system. So that I'm calling it the system ID, which is the first piece of information that you add to the lineage ID field with some delimiter. I'm using the 0-byte character here. And then the actual lineage ID is a UUID, which is universally unique because the IDs are gonna span across multiple systems, so they have to be universally unique. And most of the APIs will basically provide you a 128-bit long UUID, so that way there is no collision problem. And then you can pick any standard name for that field where you store these combination of the system ID and the lineage ID. So I'm proposing go with lineage underscore ID or something like that, but it's totally up to you what name you pick. And store it as an array. And the reason for storing that as an array is because, as I mentioned, there could be multiple upstream systems where those records could be merged into one record. Then basically the lineage of that record basically goes back to more than one record. And those individual records could have different lineage IDs. So in that case, you could basically store the lineage IDs as an array in that system. So that's the solution to the first problem. And this is again just explaining the same problem where you have two data sets. You're forming a third data set number 3. As you can see, it's an array of two lineage IDs. And then you're further deriving another, let's say, data product, call it data set 4. And then in that case, you can pick any of the lineage IDs from the upstream system, right? You still have that association regardless of which lineage ID you pick in that, for data set 4. And these are the storage rules. As I mentioned, store it as an array so that you can store more than one. And I also propose building a library, a lightweight library on an SDK that can generate the lineage ID using the standards or enforce the standards. It could be something like taking two records and then basically on the fly automatically generate that field and then attach it to that record. And then you can also build that SDK in multiple languages, depending on whether you do data processing in Spark, Beam, or something else. The solution to the problem number 2, like if you go back, like if you still remember, I had a slide with disparate data systems, and then the lineage view in the middle. That looks like a query federation problem, and Starburst or Trino basically are a query federation tool using which you can query data on demand using a unified interface and through a single query. So the only requirement is that you have to have your data sets connected into Starburst or Trino or any query federation tool that you can use for this solution. You can have your data sets spanning even clouds. You can be in a hybrid cloud model where some of the records are in one cloud versus some of the records are in another cloud. They could be in different systems. They could be in key value store or maybe RDBMSs or data warehouses kind of a solution. So you don't have to move those records anywhere else as long as you have a connector to query the records. So that was the problem number 2. So putting it all together, so this is the high-level lineage view architecture. So once you have data sets connected with a query federation tool, and once you have your records linked together across all those systems, and when there is a problem, when there is an issue that somebody has to look at, so data troubleshooter would simply go to a kind of an application which has a UI component and a backend, and then they will key in something, right? Either they will key in a primary key of the record or maybe a lineage ID if they know. And then that way the backend can go and query Starburst, and the Starburst will figure out how to get those records together. So that's the lineage view architecture that you can use as a reference to build that solution. Now, if you remember, I mentioned system ID, right? So how would system ID map to something in Starburst? So you can create a lightweight mapping of all the system IDs and the catalog name that you create in Starburst. If you know all query federation tools requires some connections that you do beforehand, and connections have names. So you can create that mapping with the IDs, system IDs, and the connections. And then, as I mentioned, the system IDs are embedded into the lineage ID. So your backend, that application backend, can basically get the catalog name, generate the query, and then issue that query to Starburst to get the information. So just considerations, when you build the lineage view, do a drill down flow. Don't try to get everything together in one go. It's going to be difficult. Read one record at a time. Have the user click on that record so that you get the next record. And then keep building that view. And then the query performance, in most of the cases or in some cases, it's hard to avoid full scan. You can do some optimization to avoid full scans. Like you can maybe add some predicates if you are partitioning on dates or something like that. You can also add, you can do clustering on the lineage ID. And if any of the data sets or they support secondary indexes, then you can have secondary indexes on the lineage ID to make the queries faster. And don't partition by the lineage ID because of the low cardinality. And I would say avoid over optimization, because this is not something that you would do day in and day out. It's probably going to be rare edge case where you run into some issues, and it's not something that you would probably do daily. So don't try to over optimize it. So we only have 1 minute. So putting it all together, so Ethan talked about a use case or a problem scenario, and then I provided you a solution which basically gives you a record level lineage capability that you can easily build in our system without building anything new, and then how that would basically solve this scenario that Ethan mentioned.
All right, so returning back to the beginning story that we all had, right? They had come to you to find out what was wrong. And now, if you have that architecture underneath you, what are you going to do? You're going to go into a system where you're going to say, I'm in this data set where it all went wrong. Here's the ID. Then you have that architecture on the back end that follows the record back and can now give you a full view of all the places that contributed to this record. And you could see very clearly with the naked eye, because for one record, it's not gonna be thousands and thousands of records here that we're talking about scanning through, dozens maybe. And you'll immediately see, okay, here's where that bad phone number came from. Here's where the bad merge happened. Now we can fix it. Goes from taking days or weeks to taking seconds. And I like to imagine then everybody starts cheering for you all around, and there's clapping, and everybody's thrilled because you solved the problem. That's right. So that pretty much sums it up.